Have you ever stared at a houseplant and just wondered, are you thirsty? Am I giving you too much water or not enough? It's a question anyone who's ever tried to grow anything asks. Well, today, we're going to dig deep into the science of how we can actually figure out when the earth itself is thirsty. We're breaking down the different ways to measure soil moisture.
I know it sounds a little out there, but what if the soil could actually talk to you? What if it could tell you exactly what it needs? In a way, it can, and learning to read those signs is one of the most important skills in farming, gardening, you name it. So how do we do it? How do we translate what the soil is trying to tell us?
All right, first things first, before we can measure it, what even is soil moisture? It's pretty simple, actually. It's just the water that's held in all the tiny little gaps, the pore spaces, between the solid particles of soil. The best way to think about it is like a sponge. The water isn't part of the sponge itself, right? It's just what the sponge is holding. Soil works the exact same way.
And why should we care so much? Because pretty much everything that makes soil alive depends on it. This water is how plants drink up nutrients, it's what determines how big a harvest you'll get, and it fuels that entire universe of microscopic life that's happening right under our feet. Honestly, without the right amount of water, soil is, well, it's just dirt.
So, how do we measure it? Let's start with the two most precise methods. These are the ones you typically do in a lab setting where getting the exact number is everything. First up is the gravimetric method. Now that sounds super technical, I know, but the idea behind it is incredibly simple. All we're doing here is measuring the mass of the water inside a soil sample and comparing it to the mass of the dry soil. It's a straight-up measurement based on weight. That's it. And the process itself is really straightforward. You go out, you grab a sample of soil, you weigh it right away. That's your wet weight. Then you stick it in a special oven, usually at about 105 degrees Celsius, for a full day. This bakes out every single drop of water. After it's cooled down, you weigh it again, and that's your dry weight. The difference between those two numbers, that's literally the weight of the water that was in your soil.
Okay, so how do we turn those two weights into a useful percentage? That's where this formula comes in. We're calculating theta G, the gravimetric water content. First, you take the wet weight, WT, and subtract the dry weight, WD. That part, WT minus WD, just gives you the mass of the water. Simple enough. But here's the key part. You then divide that number by the dry weight, WD. Why the dry weight? Because we want a stable baseline. This gives us a perfect ratio of water to soil that's comparable across any sample size.
Now that brings us to our second lab method, which is a really clever extension of the first one. While the gravimetric method was all about mass, the volumetric method is all about, you guessed it, volume. It answers a slightly different question, not just how much water is there by weight, but how much space is that water taking up inside a certain amount of soil. And this is where it gets cool, because these two are totally connected. To get the volumetric water content, or theta V, you actually start with the number we just calculated, theta G. Then you multiply it by the soil's bulk density, which is written as rho B. Now, bulk density is just a fancy term for how compacted the soil is. Is it light and fluffy or is it packed down tight? By multiplying our weight-based number by this density factor, we can perfectly convert it into a volume-based measurement. And since the density of water, rho W, is just 1, the formula really hinges on knowing your soil's bulk density.
Okay, but what if you don't have a lab? What if you need an answer like right now while you're standing in a field? That's where our next two methods come in handy. These are all about being practical and getting a quick answer. It's time to get our hands dirty.
Now we're talking about the oldest method there is, and it's based on a really simple truth. A specific soil is going to look and feel completely different depending on how wet it is. The feel test, as it's called, just takes that basic intuitive knowledge and turns it into a real technique.
And the process is, well, it's exactly what it sounds like. You dig down and grab a handful of soil. You squeeze it hard in your palm to see if it forms a ball. Then comes the real test. You try to gently push that ball out between your thumb and your forefinger to see if it forms a ribbon. The way that ball holds together and the kind of ribbon you get tells you pretty much everything you need to know.
So what exactly are you looking for? Let's say you've got a medium textured soil. If that soil is super dry, maybe under 25% moisture, it's just going to be crumbly. It won't even form a ball, let alone a ribbon. But if you're in that perfect range, say 50 to 75%, it'll form a decent ball and you can make a weak ribbon. If it's totally soaked though, it'll feel wet, make a soft ball, and you can form a really long, strong ribbon. It's definitely subjective, but someone with a bit of experience can get surprisingly close to the real number with this. Our last method uses a special tool called a tensiometer, and it measures something really fascinating called soil water suction. Here's an analogy. Imagine trying to drink a super thick milkshake through a tiny straw. The thicker it is, the harder you have to suck, right? Well, for a plant, it's the same thing. Water clings to soil particles, and the plant's roots have to literally pull that water away. A tensiometer measures how hard the plant has to suck to get a drink.
So how does this little gadget work? It's basically a sealed tube filled with water, and it has a porous ceramic tip on the end. You stick that tip down into the soil. Now, if the soil around it is dry, it's going to start pulling water out of the tube, right through that porous tip. This creates a vacuum inside the sealed tube, and a little gauge at the top measures that vacuum. A higher number on the gauge means higher tension, which tells you the soil is drier. It's a really clever way to see how much water is actually available for the plant.
Okay, so we've got 4 different methods. 2 for the lab, 2 for the field. How in the world do you decide which one to use?
This little chart breaks it down perfectly. You've got the lab methods, gravimetric and volumetric. They give you super high accuracy, but you need an oven and a scale. Then you've got the field test. 0 technology needed, but the accuracy is pretty low, and it really depends on your own judgment. And sitting right there in the middle is the tensiometer. It gives you a decent, medium level of accuracy with a pretty simple tool that you can use over and over.
When it's all said and done, it just boils down to one question. What do you really need to know? If you're a research scientist who needs a number that is absolutely positively correct for your study, you're going to be in the lab. But if you're a farmer who just needs a quick check to see if it's time to irrigate, a field method is going to be your best friend. It's that classic trade-off, isn't it? Do you need precision or do you need speed?
All of these tools, all of these techniques, they're really just ways of translating. They're helping us understand what the soil needs in a language we can finally get. So that leaves us with one last question to think about. Now that we know how to measure our planet's thirst, how can we use that knowledge to start listening a little more carefully?